Okay, so let's look what inverses, how to find inverses in Rust, how to implement it in Rust. That is what we shall be doing today. But begin by definition. What we mean by the inverse of a number. Which numbers have inverses and which ones do not. Now, so supposing we have this equation, ax equals to 1 mod m. What is x? So supposing x is b, and then what this equation is saying that x times a gives us 1. X times a gives us 1. So that means x is the inverse of a. Under multiplication, two integers a and b are inverses of each other if their product is 1. And that is what we have here. So it means if b is a solution to this equation, then it means b is the inverse of a, or a is the inverse of b. And these are multiplicative inverses. These are multiplicative inverses. We know that if it's addition, the inverse of a is b if their sum is 0. If the sum is 0, then we say that the inverses of each other. And addition. And in this case, this 0 is the identity element. Identity element. These are elements which do not make any difference on other elements. We'll be looking at this when we begin looking at groups and rings. So we'll be looking at the properties of groups and properties of rings. Now, so 1 is also the identity element under multiplication. That means any element multiplied by 1, the result will be that element. But what we're interested in is the inverse. An element times another element, if the result is the identity element, then those two elements are inverses of each other. Under multiplication and under addition, these two elements are inverses of each other if their sum is identity 0. So if A has an inverse, then we say that A is invertible. In other words, you can get its inverse. And if C has an inverse, you also say that C is invertible. Now, under this modular arithmetic, elements that will have inverses mod m, elements that will have inverses mod m are those which are relatively prime to m. Elements which are relatively prime. Relatively prime. Any other element that is not relatively prime to m would not have an inverse. And of course, we know what we mean by relatively prime or coprime. We say that two elements are coprime or are relatively prime if their GCD is 1. If their GCD is 1. If the GCD of A and M is 1, then we say that they're relatively prime. A is relatively prime to M, or we say that these two are coprime. The other way of defining that is saying that A is relatively prime to B if the only common factor is the common element and divide A and M is 1. So we say that A is relatively prime to M, or A and M are coprime. For instance, when we talk of mod 9, then elements that would have inverses, elements that will have inverses mod 9, 1 is one of them because it's relatively prime to 9. 2 is another. 3 is not relatively prime to 9. 4 is relatively prime to 9. 5 is relatively prime to 9. 6 is not. 7 and 8. So these elements would have inverses. These elements would have inverses. In fact, how many are they? They are Euler phi of M. We have defined what Euler phi of M is. These are elements less than M and relatively prime to M. Elements less than M and relatively prime to M. Euler phi of M. So how many are they? 1, 2, 3, 4, 5, 6. Euler phi of M is 6. So there are 6 elements which are relatively prime. 1, 2, 3 is not. 4, 5, 6 is not. 7, 8, yes. There are those 6 elements. So this would have inverses. So I don't expect 3 to have an inverse. 3 cannot have an inverse mod 9. Cannot. That inverse does not exist. Is not there. That inverse is not there. But 2 would have an inverse. So what we were interested in is now finding the inverses. Finding the inverse of 2. That means finding an element which, when multiplied by 2, gives you 9. And that element must also be less than 9. That inverse must also be less than 9. In fact, the inverse of 2 is 5. The inverse of 2 is 5. Because you can see 2 times 5 is 1 mod 9. 2 times 5 is 1 mod 9. So therefore, the inverse of 2 is 5, and the inverse of 5 is 2. Now, so let's just go through the steps of finding inverses. Somebody might be wondering how we got how we knew that the inverse of 2 was 5. There are various methods, and one of the methods is Euclid's algorithm combined with the extended Euclidean algorithm. When you combine those two, you can find inverses of elements. The first thing you do, you find the determinant. Find the determinant, not the GCD, not the determinant. GCD of 7 and 9 and 19. If this GCD is 1, as we already said, then it means that 7 has an inverse. If the GCD is 1. The fact, when you're writing when you're writing that Rust code, this is the first thing you do. You include the extended Euclidean algorithm. Extended, so that code will have 2 functions. We'll have the function to calculate the GCD. And of course, after calculating GCD, write that GCD in terms of the elements 7 and 19. So find the value x and y so that 7 times x plus 19 times y gives you the GCD. So that function must be there to find the GCD. And then that function, after finding the GCD, you then must have a function to do inverse. After finding GCD and writing and obtaining the values x and y, You must then have function for the inverse, mod inverse. And what this function will be doing, first of all, is to check whether the GCD is 1. If the GCD is 1, then it comes straight to this and gives you the inverse. Comes straight to this. What the extended Euclidean algorithm has already done, goes there and then picks the inverse for you. If the GCD is not equal to 1, it tells you that there is no inverse for that function. So if you're writing the extended Euclidean algorithm again, and when you're writing that code, that Rust code, these are the steps. So the first step, you'd have the function to do the extended Euclidean algorithm function. It will begin by finding the GCD. So how did we do it here? That is what it will be doing. You have 19 and 7. It asks 7 into 19 how many times? Twice. The remainder is 5. This 5 into 7 how many times? 5 into 7 once. The remainder is 2. 2 into 5 how many times? 2 into 5 twice. The remainder is 1. So that is what that function will be doing. Then it comes up to here until b is 0. So that will be happening until b, that loop will happen until b is 0. When b is 0, it exits. After exiting, it comes and does this reversing. You'll be doing this reversing, beginning from the GCD. The GCD is 1. So the GCD can be written as 5 minus this. When you take this on the other side of the equal sign, this GCD, which is 1, is 5 minus this. Then replace this remainder. So it will again be replacing. I'll show you how it will be working. It will replace this remainder, which is 2. Its equivalent is 7 minus 5 multiplied by 1. So we have this 5. Then you have 2. This 2 is here. And this other 2 is the remainder, which is 7 minus 5 multiplied by 1. 7 minus 5 multiplied by 1. So when you cross it to the other side of the equal sign. And then after that, you open this bracket. The 5 is still here. When you open the bracket with this 2, and there's a minus outside here, that would be minus 2 multiplied by 7. And this minus and this will be positive, multiplied by this 2, positive 5. And this 1 times this 2 just be 2. Then collect like terms. There's this 5 and there's this 5. So what we have here, this is like 5 with a 1. Then it's 5 with a 2. The common term here is 5. What is inside the bracket is 1 plus 2, which is 3. Which is 3 you're seeing here. Now, so we've already replaced this 1. We've already replaced this remainder, which is 2. We are left to replace this 5. What is 5? That is now what we replace. 5 is 19 minus 7 multiplied by 2. When you take 7 multiplied by 2, the other side of the equal sign, you substitute 5 with that. So this part is here. Then 19. So we're just replacing 5. 5 with the 19 minus that. 19 minus 7 rest multiplied by 2. Then this 3 is here. Again, you open this bracket. There's a positive sign, and there's this 3. So you begin with this negative 7 multiplied by 2. But now 3 multiplied by 19 is here. And then 3 multiplied by 2 here will be 6. Then multiplied by 7. That's what you get. Then collect like terms again. You have this 7 and you have this 7. And what is inside the bracket is 2 and 6, which gives us 8. So what we get there is 19 multiplied by 3, and then negative 7 multiplied by 8. But now 7 was positive. 7 was positive. So that means what we have is 19 multiplied by 3 plus 7 multiplied by negative 8. That is what we end up with. Now, so when we reach here, what we wanted was the inverse of 7. So the inverse of 7, therefore, is negative 8 mod 19. But we want positive answer. So since we want a positive answer, we add this to that. And that is when you're writing your code again, you remember that, so that your answers are positive. Otherwise, you'll be giving you negative results. Where there's a negative result, you'll be giving negative results when it's supposed to be giving you positive. So this gives you 11. 11, therefore, is the inverse of 7. Mod 19. So the inverse of 11 mod 19 again will be 7, and so on, that way. So the other example, I'll not go through it because we had done this, these calculations. So I'll go straight to the code. Then we see how it works. I've already said the code will have what we've already explained here. It will have the Euclidean algorithm, the function to perform Euclidean algorithm, so that it be giving us the GCD, and then after that, express that GCD in terms of the two coefficients. To write that GCD as a linear combination of the two numbers. The two numbers, in this case, 7 and 19. So it will find the GCD of 7 and 19, then write that in terms of, just the same way we've done here. The same way we've done here. In fact, we converted this to positive. So we wrote it as, this is how we wrote it. This is how we wrote it. 1 is this 19 multiplied by 3 plus 7 multiplied by, this became 11. This became 11. But it can, you see, when you are doing that Rust code, the Euclidean algorithm will come up to here. Will come up to negative 8. It will end here. And then the inverse, the mod inverse function picks from here. The mod inverse function comes and reads the GCD. After reading the GCD, it comes and converts this the way we did to give us 11. So that will be the function of the mod inverse function. Then, of course, we have the main function that will have these two functions calling each other there. You look at this example later. You look at this example, just what we've done, it's the same process. Finding the GCD of 364 and this. And this question is asking you to find a value x. In other words, it's asking for the inverse of 364 mod 765. That's what the question is asking. It's telling you, find a number x, which when multiplied by 364 gives you 1. And that is how we define the inverse of a number. We defined it to be another number which when multiplied by a gives us 1. Now, so we've already seen how the code is supposed to be. We've already said the code will have two functions, just as we've done those examples. So the following Rust code defines two functions: extended GCD, that extended Euclidean function, and then the mod inverse function. And those are the functions which will be assisting us to find the inverse. So the first one is the extended. Of course, when you are doing that, you begin from where we have the main function. You would even have put it at the top. There's no problem. I decided to put it here. Now, so in the main function, you define the two integers you want to get inverses to. You want to get the inverse of a mod m. So you let your a be, in this case, 364, the example that has just been above, and let m, which is our modulus, that. Then we want to get the inverse of a mod m. So this, what this main function will do, it will call on the mod inverse function. And the mod inverse function, so it calls on the mod inverse function with the two numbers. And the mod inverse function is here. The mod inverse function would call the extended GCD function. So this one calls the mod inverse function, and the mod inverse function calls the extended GCD function. So that is where we go to begin from. Want to begin from there. That is now what begins. Because the mod inverse function was called, but then it calls the extended GCD function. So the extended GCD function begins. Then where it ends, now the mod inverse function takes over, and then back to the main function where we now print. Now look at this. After that, if there is some inverse, this code will print the modular inverse of a modulo m is, so it puts the inverse here. So if there is some inverse, then it will print the modular inverse of a modulo m is, and you can see that here. So the first bracket is a, the second bracket is m, and then finally we have the inverse. Now, we have said that if a is not relatively prime to m, then there will be no inverse. So in that case, none, where there is no inverse, it will print the modular inverse does not exist. The modular inverse does not exist. Just 1 minute. Okay, so that is the order in which this code will be working. We've said the first thing, when we enter the main function calls on the mod inverse function. asking it to get the inverse. And the mod inverse function knows that the extended Euclidean function should first of all work out the GCD and then express that GCD in terms of the in terms of constants x and y, coefficients x and y. And then after that, the mod inverse function takes over now to find the inverse. And then we go back to the main function, and then which then prints the results. So let me just share the code so that we look at it. Okay, the code is here. You can see it.
Yes.
Okay. I've defined for I64. You can always, as we've always said, you can change this to 128, 1 or 32, or even smaller. Of course, the highest it can go if you are using this format is 128 bits. 128 bits. You can see that it's I. You're not using U. It's I because we expect to be dealing with the negative numbers and positive numbers. So we'll be dealing with both positive and negative numbers. And that's why. So our main function, as we've said, is here. It has, this is the way we put initial values, our A and M, and then it will be calling for the mod inverse function with the A and M. And then this mod inverse function would be called the extended GCD function. And what this extended GCD function is doing is finding the GCD. And then if the GCD is G, that GCD will be written in terms of A and B. So it will have again obtained values X and Y. X and Y, so that the GCD can be written as A times X, A plus Y times M. Now look at what the extended GCD function is doing. It begins by saying, now, so in this case, we had A and M. So M becomes B. M becomes B, and A is just the A we had. Of course, they'll be, they're mutable. They'll be changing with the time, they'll be changing. So what happens if B, which is our M, is 0, then we get this result. What this result means is that if B is 0, the GCD of A and B will be A. That's what it's saying. That if A and B are 0, B is 0 and A is a number. So like we have 7 and 0, and you're getting the GCD. The GCD will be 7. So the GCD will be A. That is what this is saying. Saying if B equals to 0, then GCD is A. And if you're writing GCD in terms of A and B, where B is 0, then X is 1 and Y is 0. X is 1 and Y is 0. So that in case you have, let me say, in case you had, let me just type here. In case you had 7, as A. In case A was 7, and in case that B is 0. So what then this means is that the GCD of A and B, the GCD of A and B, GCD of A and B will be A. Will be A. So that is what this thing is saying. And if that is the case, it's also saying that then the coefficient of A will be 1, so that we can write 7 is equals to, our A is 7, its coefficient is 1. Its coefficient is 1. And then B was 0, its coefficient will also be 0. So that our GCD has been written in terms of the two numbers A and B, and we've obtained X and Y. So X is 1 and B and Y is 0. That is what this is telling us. If the GCD is, if M is 0, and in fact M becomes B in terms of calculating the GCD. Else here means if none of the numbers is 0, if none of the numbers is 0, if B is not 0, then we proceed with the Euclidean algorithm. And I like what it's calling, what it's doing here. Look at how the numbers are changing. We had A and B, so we are finding the GCD of A and B. It calls for B, and this is the remainder of A on division by B, the remainder of A on division by B. So I'll show you how that works. And then this process, B is changing and A is changing. This process continues until B is 0. The process continues until B is 0. When B is 0, you can now find the GCD. And after you found the GCD, come to the mod in, no, after you reverse and get X and Y. Reverse and get X and Y. The formula for finding X and Y is here. This is the formula. Now, what is this formula saying? The formula is saying, I just want you to understand what the formula is saying. The formula is saying that after this process, what you have here is GCD. X, look at this, just look at this one here, this part, the part I have highlighted. GCD, comma, X, comma, Y. So our GCD is still here, G, but X is replaced by Y. And Y is replaced by X minus A divided by B, and then the result, you only take the whole number. The result multiplied by Y, and Y is coming from here. Y is coming from here. That is what this formula is saying. That the GCD, and how do you get X? X, you just take the Y which was above, make it X, and Y, no. I'm saying that X, you take Y. So Y you make it X. And Y becomes X minus A divided by B multiplied by Y. And I've said when you're multiplying A by B, you only take the whole number. For instance, 7 divided by 3, you only take 2. 7 divided by 3, you take 2. So 3 goes into 7 twice. Now, once you reach B0, and you want the inverse function, and then inverse function begins from let. Look at that. Let. What it's saying, it's what we just obtained here. Referring to that, let GCD x, the value of x from here. And then it GCD function was the GCD of m. So the value out here, we just value of oh, I went off, huh?
Yes, just a bit.
Okay. So I was explaining what is happening at the modular inverse function. Hello, can you hear me?
Yes.
Okay. Now, so after we receive values from this function, we begin from here. If, look at this what I'm highlighting. It means if GCD is not equal to 1, that's what it means. If GCD is not equal to 1, then the modular inverse has no inverse. No, the modular has no inverse. Has no inverse, so none. That means this will be printing. This one will be printing the modular inverse does not exist. The modular inverse does not exist. That means if the GCD is not equal to 1, that is what this symbols. That means if the GCD is 1, the value of x, which came from above, if it was negative or positive, we are adding. Look at this. This is x, the remainder of x on division by m. Then that remainder, add m to it to ensure that if it was negative, you're making it positive. The result that you get, again, divided by m and write the remainder. So the remainder of that, the remainder of whatever is in this bracket on division by m. That is what this symbol means. And then, so that is now the result. That is the sum result, which is then printed here. That is what we print there. So let me just run this. Run it. Okay. It says, you can see the result, huh? What I'm highlighting. Can you see it, or it's hidden?
The modular inverse, yes.
Yes, of 364 modulo 765 is 124. Let us change. I said those two numbers should be relatively prime. Let's try number that's not relatively prime. Let's try 365 and see if it will give us an inverse, because they're not relatively prime. If it gives us, that means this thing has not been well done. Okay, it discovered those numbers are not relatively prime. It has written here, the modular inverse does not exist. The modular inverse does not exist because it has noticed those numbers not relatively prime. Of course, it went through the whole process, although very fast, but it went through this process, the extended decline algorithm, found the GCD, and then discovered that GCD was not one. So at this point, if GCD is not equal to one, this then prints none. And so it prints modular inverse does not exist. Let's try to increase these numbers. Let's just try to increase. And we know that when we increase, if it refuses to work, and then I don't know whether the number we increased to are relatively prime, but it will tell us if they are relatively prime or not. Because I was just typing. Oh, the number is too huge. It's beyond the range of I-164. So let's reduce the numbers just to be in that range. You can see if it goes beyond the range, then we go to big integer. You go to the big integer library and use it. Of course, we can also make it, we can make it 128 if you want. You can make, instead of I-164, you can make it I-128. Oh, these numbers are relatively prime. It says the modular inverse does not exist. So they're relatively prime. Let me try and make it 3 here and see if they'll still be relatively prime. If I put a 3, if I put a 3, the modular inverse is there. Let me just reduce this. Let me just print it again. Yes, it says the modular inverse of this integer, modulo this, is that if I make it 3, so they're now not relatively prime, but as they were relatively prime at that point. Now, of course, if you want to change it to, you can change this to I-128 or to big integer and deal with the very huge numbers. Now, let me look at an example that will require that. There's an example that I had that will be requiring the use of big integer. The example is here. The example is compute the inverse of this number. This number is very long. Compute the inverse of this number. And the modulus is also long. So our I-68 cannot manage this. Our I-68 cannot manage it. So I'll go straight to big instead of using I-128. It may also fail. Now, so the following Rust code offers functions for calculating modular inverse of huge integers. So the library, we shall be using the num big integer. This one handles large integers. And when we run that code, the code that is just below this, we get this as the inverse. This becomes the inverse. Now, the code is just the same as the one I've explained. The one I've explained is simpler to understand. But it's the same code. The only difference is that you import these libraries, import those libraries, and you can see where I had I164, I've just replaced it by big integer, while there was I164, I've just replaced by that. The rest remain the same thing. We have, I just reversed this too, but there's no problem. Any function can begin. This was the function of the inverse. In the previous, it was, I had placed it here. And of course, we also said we can even begin with this main function up here. So there's no problem. So long as they know which one follows which. Now, so the extended Euclidean algorithm is just the same as the one above. The only difference is that where there's I64, I'm just putting big integer, and so on. That's the only difference. That's the same way we would put there 128, I128, or I32 and so on. But the rest, okay. I've put wrap and wrap just to ensure that there is no overflow. And then it will print the modular inverse is this, if there is some modular inverse. And if there is no modular inverse, it will print no modular inverse exists for the given integer. Now, so it's here. These are the integers. You can see the numbers, huh? The main function. The one I'm highlighting.
Yes.
Okay. So the main function calls on the modular inverse function. And the modular inverse function calls on the extended Euclidean function. The modular inverse function is here. It calls on the extended GCD function. And the extended GCD function takes over and then computes the GCD. Let's run this. It says the modular inverse is this. So it has given us the modular inverse for this integer. We can increase it a bit, only that sometimes it will take long. So if it discover it takes long, we stop it, but that we can continue with other things. I don't know whether they're relatively prime. Of course, they can only work if they're relatively prime. That's running this. Oh, it has given us the inverse is this. Of course, you can make it even longer, only that it will still run, but it will take time. Of course, there'll be no overlap because of the unwrap. So the unwrap is taking care of that. The unwrap is taking care of that. Okay, so let me now just explain how the code works to calculate the inverse. Of course, just the same thing we talked about. Now, so I'll begin the extended GCD function. Of course, the main function does not have much. The main function only has a point where we inputting the values A and M, and then it also has a point where it calls on the modular inverse function. Then it has a point where it's printing the results. So let's begin with the extended Euclidean function, extended GCD function. Now, so this function, as we already said, has two roles. The first role is to compute the GCD. And the other role is to determine the coefficients X and Y, so that this GCD can be written in terms of A and B. So the GCD can be written as AX plus BY. So that is what the extended Euclidean function will be doing. So it's here, summarized here. Summarized here. So of course, we've said it, we are using the I64, we know what it means. But then it begins by saying, if B is 0, we had already explained that if B is 0, you see M becomes B. And then there is this A. So if B is 0, the GCD is A. And the coefficient of A is 1. And the coefficient of, so X is 1 and Y is 0. So that's what I've written here as the best case. The best case. That's what I've written here. The best case means that it says if B is 0, the function returns this. Because, for instance, if you are to take n to 0, the GCD will be A. The GCD will be A. And the coefficient will be, the coefficient of A will be 1, and the coefficient of B will be 0. So that this sum gives you A. So that is this first bit. That is that first bit. And so that is what is here. I've put it here. That first bit, I've put it here. So the coefficients are written here. The GCD, X and Y. The GCD, X and Y. GCD is A in the case where B is 0. Now, if B is not 0, then we begin with the Euclidean algorithm, finding the remainder at every stage as we proceed. So that is what it will then be doing. If B is not 0, we begin the recursive case. The recursive case, if B is not 0, the recursive case begins. So the function calls itself. Let us see what it's doing. It's calling itself. Yes. Else, it calls itself. You can see the function GCD, extended GCD function calling itself now. One, after realizing that B is not 0. It calls itself and then calculates the coefficients. It calls itself with B and the remainder of A on division by B. And this process of calling itself with B and the remainder of A on division by B continues until B becomes 0. So it will only stop when B is 0. That is one point. So if B is 0, then we have the GCD. It has obtained the GCD. Then it begins reversing. To calculate the coefficients, it has to reverse. So the recursive case, the recursive call returns the GCD and the coefficients of x1 and y1 for the equation that involves b and the remainder of a on division by b, where x will be y and y will be x minus a divided by b multiplied by y. And at this point, I said it will only be taking the whole number. If a is 7 and b is 3, it's just that division is 2. So it takes 2. So x1 minus a divided by b multiplied by y1. I'll show you how that works with an example. Now, once the GCD, the extended GCD function is done, the mod inverse function takes over. And the mod inverse function computes the modular inverse of A, mod M. And you see that inverse is just the value modular by A to give you 1. So how does it begin? It uses the extended Euclidean algorithm, the result obtained above by the extended Euclidean algorithm, to find the GCD. Then after finding that GCD, if the GCD is not equal to 1, that is what this means. If the GCD is not equal to 1, then it says none, to mean there is no inverse. So that is why I've said here, it checks for inverse existence. If the GCD is not 1, then A and M are not coprime, and therefore there is no modular inverse. That's what this one writes here. If G is not equal to 1, this is how Rust calls it. But you know, in mathematics, sometimes it's this. If G is not equal to 1. So this is the Rust way of writing this, not equal to 1. Now, but if G is 1, if G is 1, then it will now give you the inverse. And I said the reason for M dividing by M here, and the reason for adding M, and that is just to ensure that the results are positive. To ensure that the result is given is positive, so that we don't have negative results. I want to show an example how that function would work, just very fast. Let's look at the inverse of 31 and 60. So we just want to move the way that function moves, slowly by slowly, until we find this result. Now we have the main function. We input A and B and M. That is the main function. Then this main function calls the mod inverse to find the inverse of A mod M, where A is 31 and M is 60. The mod inverse with the same numbers, and then so that the extended GCD function gets the GCD and gets the coefficients. So that is what the main function, what we write in the main function. And then the main function will then, of course, at the end, will be printing the results. Now, so then it means after the main function, the GCD takes over. The GCD Euclidean function takes over. The initial call, this is what it it calls extended Euclidean 3160. 3160. And let me just take you back to the code so that as we move, you know what we are saying. 3160. Let's just go back to the code. Where is it? It's here. It's here. Let me just use this. This is the extended function. Or let me use this other one, is easier to see. The other one is easier to see. Yeah, good. Now, in ours, we have A as 31 and now B as 60. So this is what this is where we are. This is a case where B is not 0. B is not 0, so we are past this part. We are past that part. We come here. We may go back here. When B becomes 0, finally, we'll go back there. When B becomes 0, because this process has to continue until B is 0. So when B is 0, we'll go back and use this part. But we begin from here. Look at what it talks about. When it calls of the GCD, extended GCD of 3160. This is what it calls. Then, what is the result? What is the result here? Look at the result. Look at the result. The result of this calling, the result of this call is B, in this case, 60. And then the remainder of A on division by 60. The remainder of A on division by 60. What is this? What is this? This is 60. The remainder of 31 on division by that is 31. So the result of this is this. That is the initial call. Then there will be next call. The next call, it will be calling the extended GCD of 61, 60, 31. But what is the result? What is the result of this? Result of, look at this, just interchanges. A B becomes A. What was B here becomes A. What was B becomes A. In this case, our B is now 31. Okay. We have a new B. You can hear me, is that okay?
Yes.
Yes, so I'm just telling you how it works. What was B becomes A. So this is our B becomes A. What was now our new B is the remainder of 60 on division by 31. The remainder of 60 on division by 31. So you see, this is what we normally do, what we've been doing in the earlier process, where we just write the remainder and the remainder. You see here, the remainder is 31. Now, this will be 31. When you divide 60 by 31, the remainder is 29. The remainder is 29. Then there will be the next call. The next call, it calls on extended GCD of 3129, 3129. But what is that? What is that? according to this formula, is B, which is 29, then the remainder of 31 on division by 29. The remainder of 31 on division by 29. I'm just reading this formula here. And what is this? This is 29. And when you divide 31 by 29, the remainder is 2. So you see, just writing the remainders, you see the previous case that we were doing is just the same thing. What we used to do was 60, 31 into 60, how many times? That's what we were saying. Let me write it here. It was 31 into 60, how many times? And they would say, because they are 1, and the remainder is 29. It's this 29 you are seeing here. And then we would say 29 into 31. I want you to see the relationship. We would say 21 into 39. How many times? We would say goes there 1, and the remainder is 2. And that is this process. The process you're seeing there, 29 and 2. 29 and 2. And we just say 29 into 31. How many times? 20, and what is the remainder? Then the next calls the extended GCD of 29 and 2. And what is this? This is, and I'm using this formula. B is 2. And then the remainder of 29 on division by 2. And the 2 will go there 14 times. So this would mean 1. It will mean 1. The remainder is 1. And of course, that is what is happening here. The normal way we've been doing it, we would say 2 into 29. How many times? And we'll say 2 go there 14 times. And the remainder is 1. That is what we've reached. And then lastly, it calls on GCD, extended GCD of 2 and 1. And what is that? What is that? This is the same as 1. Then the remainder of 2 on division by 1. What is this? This is 1, and the remainder here is 0. B has become 0. B has become 0. What does it say? When B is 0, we go back to the base. When B is 0, our GCD is A. Our GCD is A. In this case, when B is 0, because we have this point, B is 0. So our GCD now is A. And it also talks about an X, which is 1. And then it also talks about a Y, which is 0. So that is when we exit the extended GCD function. It has obtained the GCD, it has obtained the coefficient of X and 0 and Y. But from here, we start going up. We start going up now, reversing the recursive process. Now we reverse the same way we normally reverse, And you see for this case, we would have begun from here reversing. We began from there when the remainder was 1. When the remainder was 1, because the next step will be what? 1 into 2. Yeah, I just reversed, I reversed it. The 1 into 2, which will be the remainder will be 0. So the reverse from when the remainder is 1, that point, when the remainder is 1, is here. That point is here. When the remainder is 1. Now, what does it say? What does it say to reverse? Let's just clear this so that we see what we are doing. Just clear this. We've seen how to find the GCD. It's a very easy thing, just the same way we've been doing. This time only that we are moving with the two numbers. Now, what does it say? You see, we are coming with this. We are coming with this. It says, let GCD X and Y. So we're just saying let GCD, which is 1, X, which is 1, and Y, which is 0. So if that is the case, what will be Y? What will be Y, the coefficient of X? And what will be X? Now it says X becomes Y. X becomes Y. X becomes Y. You can see what I'm pointing at. Eh?
Yes.
X becomes Y. And what is Y? Y is 0. So in that case, X is 0. What about Y? What about Y? Y becomes this. We are at when the remainder is 1. So in this, when the remainder is 1, 2 is our A, and our B is 1. So what is Y? Y, let me talk of X1 and Y1 so that we don't confuse. X1, Y1. So, but what does Y1 become? Y1 becomes X, which is 1. X is 1 here. Then minus, our numbers are 21. That is where we are, 21. So 2 divided by 1. 2 divided by 1. Then multiplied by Y. But our Y is 0. So when you do this, inside the bracket, you have 2 multiplied by 0. That would be 0. So Y becomes 1. Y becomes 1. So what we now have is that X1 is 0 and Y is 1. But the GCD is still 1. The GCD is still 1. So we are leaving that point with the 1, 0, 1. Then we move to the next remainder. The next remainder, when the remainder was 2, this point, when the remainder was 2, we are moving from down going up. When the remainder was 2, our A was 29 and our B was 2. We are going there with this. We are going there with this. Just clear this part a bit. I just want to work from here so that you see the formula. You look at the formula as we go, but you look at my workings. I have the workings down there. So I want us to refer to the formula that the Rust is using as you see what the formula says. Now, so we've obtained our X to be 0 and our Y to be 1 and our GCD is still 1. We are moving at this point when the remainder is 2. So our new X, still the formula says X should be equal to Y. X should be equal to Y. but our y is 1. Our y is 1 now, so x is 1. What about y? The formula says y should be equal to x minus a divided by b multiplied by y. So x is 1. What is x? No. X is 0, the one we have come with. The x that we've come with, not the one we've obtained. This is our new x, but we are referring to the one we've come with. We've come with 0. And what about a? A is 29. Then divided by 2. Then multiplied by the y that we've come with, which is 1. What do you get? This will be 14, negative 14. Negative 14 times 1 will be negative 14. So now, what are we living here with? At this point, we are living this point we've obtained. Our GCD is still 1. We've obtained a new x, and we've obtained a new y. Obtained a new y. We now move to the next remainder. And the next remainder was what? It was 29. The next remainder was 29. I don't know whether we've looked at all the remainders, but I think we've looked at this, looked at this. Okay, the next one is 29. Yes, the next one is 29. But we have 31 and 29 at that point. We have 31 and 29 at that point. So I want you to get what you're saying. What are we going there with? We are going there with this. GCD, which is 1, our x, which is 1, and our y, which is negative 14. We want to obtain the new x at that point. The new x at that point will be equal to y, but the y that we are going there with is negative 14. So the new x coefficient will be negative 14. What about the new y? The new y would be the x that we've gone there with, which is 1, then minus, where are we? We are 31 and 29. So 31 minus 31 divided by 29, multiplied by the y that we've gone there with. The y that we've gone there with is negative 14. So what does this give us? This is 1. 31 divided by 29 is 1. So that 1, there's a negative here, will be negative 1 multiplied by negative 14, which will be 14 plus 1, that gives us 15. So what have we obtained at this point? We have obtained GCD is still 1. We've obtained a new x, which is negative 14. We've also obtained a new y, which is 15. So that is what we've obtained. Then we move to the final point here, where the remainder was 31. This is now where we move. That is the final. We've been moving from bottom going up. Okay. What are we coming there with? We are coming there with the GCD, which is 1, our x, which is negative 14, and our y, which is 15. So what is our new x? Our new x will be, of course, equal to the y that we are coming there with, and that y is negative 14. And then the new y will be the x that we are coming with. Y is 15? Y is 15? Y is 15? Y is 15. So that is our new x. What about y? Y will be the x that we are coming with, then minus, I'm just referring to the formula, a divided by b. A is 60 and b is 31. The remainder is what we want. The remainder is what we want. The remainder will be 29. So 60 divided by that, the remainder will be 29. And that remainder multiplied by y. Y is 15. What is that remainder? 60, 31 into. Is it, the remainder is 29, huh? Okay, what was the question? Okay. Now, what do you get when you multiply this?
That's 48 point. Oh, it's 14 times.
This number appears big. Oh, so I was mute. Thank you. So I was saying that because of time, I just share the workings. We look at them. Tomorrow when we get time, we can look at them again. And tomorrow I also had the feeling that we can begin looking at the groups and functions also, so that also we have that knowledge of groups and rings and so on. So this is where the extended you are reversing, and that is what I was doing above. That's what we were doing. Okay. So you look at it, that is how the code works. Good. That's the end of the class.